Have you ever stopped to think about how our messy, creative human ideas get turned into perfectly logical instructions that a computer can actually follow? Well, we're about to pull back that curtain. We're going to take a journey from the code a programmer writes all the way down to a command a machine can execute. Okay, let's just dive right in. Look at this. To a programmer, this line of code is super simple. But you have to remember, a computer only gets on and off, ones and zeros. So to the machine, this is basically a foreign language. How on earth does it bridge that gap? How does our alphabet become its binary?
Well, the secret? It's all about translation. Honestly, think about it just like learning a new language yourself. You can't just pick up a book in another language and instantly get it. Nope. You have to learn the words first, then the grammar, and then you can start to understand the meaning. A computer does the exact same thing with code.
And this whole translation thing follows a really clear three-step roadmap. First, the computer has to identify all the individual words and symbols. Then, it checks if they're all arranged correctly, following the grammar rules of the language. And finally, once it knows the sentence is built right, it can figure out what it's actually supposed to mean. So words, grammar, and meaning. Let's break each one down.
First up, step one, the words. Before you can understand a sentence, you have to be able to see where one word ends and the next one begins, right? It's the same for a computer. And in the world of programming, we call these words tokens.
So a token is the smallest meaningful piece of the puzzle. And think about it. In English, a sentence isn't just words. You've got punctuation, like commas and periods, that are absolutely essential for structure. Well, in code, all of those little individual pieces, the words, the numbers, the symbols, they're all considered tokens.
Okay, let's see this in action. The computer doesn't read the phrase int score equals 100. Instead, it chops it up into 5 distinct tokens. First, there's int. That's a special keyword that tells the computer what kind of data is coming. Then there's score. That's the name or the identifier that we've given to our little piece of data. Then you've got the equal sign and operator that assigns the value. You got the number 100 itself, and finally that semicolon, which is a separator that basically acts like a period at the end of a sentence. This whole process, by the way, has a name. It's called tokenization.
All right, so let's move on to step 2. Once the computer has its list of all these tokens, it needs to figure out if they're in the right order. This is the grammar check, or what programmers call checking the syntax. You see, every single programming language has a super strict set of grammar rules. That's its syntax. You can't just throw tokens around wherever you feel like it, any more than in English you can say, house blue is the. There's a correct structure, and you've got to follow it. And this is a perfect example of what I'm talking about. On the left, int age equals 30 follows the rules perfectly. You have the type, then the name, the equal sign, the value, and the semicolon. It is syntactically correct. But look at the right. It's the exact same tokens, just all scrambled up. To the computer, that's just grammatical garbage, and it'll immediately throw a syntax error. Now here's the crucial point. At this syntax stage, the computer is basically just a glorified pattern matcher. It has absolutely zero understanding of what the code is trying to do. It doesn't know what age is for, it doesn't know that 30 is a number, it only knows that the sequence of token types is valid according to its rulebook. That's it. And that brings us to our final and maybe the most fascinating step, actually understanding the meaning. Now that the computer knows the grammar is right, it has to figure out the logical intent of the code. And this is the world of semantics. Semantics is all about logic. A program can be grammatically perfect, but it can still be total nonsense. So during the semantic check, the computer is essentially asking itself, okay, this sentence is put together correctly, but does it actually make sense? You might have heard of this famous example from the linguist Noam Chomsky. Colorless green ideas sleep furiously. Listen to it. Every single part of that sentence is in the right grammatical spot. You've got your adjectives, your noun, your verb, your adverb. The syntax is absolutely perfect. But the meaning? It's complete and utter gibberish. That's a semantic failure. And the exact same thing happens in code. The example on the right is grammatically valid. You can try to add two things together. But the semantics? Oh, they're a total disaster. You can't logically add a word to a number. It's like trying to add the color blue to the sound of a bell. It just doesn't make sense. The computer sees this as logical nonsense and flags a semantic error. So why does any of this matter? Why go through all this? Because this three-step process, tokens, syntax, semantics, this is the fundamental bridge between our creative, sometimes chaotic human minds and the cold, hard logic of a silicon chip. It's how a simple idea becomes a direct command.
So let's just recap that journey real quick. First, the computer breaks our code into individual words and symbols, the tokens. Next, it checks if those tokens are arranged according to the language's grammar rules, the syntax. And finally, it analyzes that grammatically correct sentence to understand its logical meaning and purpose, its semantics.
And here is the truly amazing part. This whole intricate process of translation, it isn't happening slowly. It's happening at a speed that's almost impossible to imagine, billions and billions of times every single second, right inside your computer and your phone. It is the invisible engine that powers literally everything you use. Which kind of leaves us with one last big thought. If code really is a language with its own words, its own grammar, and its own meaning, then it's the language we use to have a conversation with technology. So the real question becomes, as this language gets more and more powerful, what more interesting conversations should we start having with our machines? Something to think about.